Okay, good morning. So now it's time we should start today's lecture. Yep. So on Tuesday, we mainly derived two main results. So we have two main results. First one, we introduced the first law and second law, and the more important, a key theme in our statement about the second law is any changes, if it happens, then adiabatically there's no internal heat flow going into the system or the heat going from the system to its environment, then the entropy change must be equal or greater than zero. The equal sign happens when it's a reversible change. The greater sign happens if it's a non-spontaneous change that going through non-equilibrium states. Second part is we derived the fundamental equation for thermodynamics that connects change of total derivative of energy to entropy and some force reversible terms. Okay. And from there, if we consider PV work, if it's a gas system, normally PV work is important. And also we consider chemical work that is related to change in the chemical species in concentration or number of chemical species. In that case, this work will have two terms: PV work and some chemical work measured by chemical potential. So this will become TdS minus PdV. This minus sign comes from the definition of directionality. Okay. Plus summation all the chemical species and mu I, d, and I, and their number of particles. How many more changed? Okay. And R here is the number of number of chemical components.
老师有要分享荧幕吗？
Sorry, I forget to. Thank you. Yeah. But luckily, all those equations have been. I wrote down this before on Tuesday already, so you should easily see this. Okay, so this R here is the number of chemical components in the system, and for simplicity, later on this part will simply be written as mu dn. Okay, it looks like it's for one component system. For one component system, only one chemical potential and one change in the number of particles, but it can be easily generalized to multiple component systems. So I'm not going to write this summation all the time. And recall this is derived for reversible changes, meaning it's for equilibrium states. Okay, so those are the two main results we obtained so far. And later on, we will focus on the consequence of these two main results. Okay, so up to here, is there any questions? I saw that on the class log last week, on Tuesday, someone asked a question. I'm going to share. 洪世恒，你要不要问一下？
哦，好，就是I'm wondering whether we have to use the substituted partial S, and
so the question, so I will just rephrase it. The question is, if we know Q reversible work equals to T. I'm sorry. If we know ds is TQ reversible, then, and also change of energy is reversible or plus reversible, then why can we just substitute this and come up with this equation? Is that your question, right?
Yeah.
Yes. Okay. The problem is actually it's the opposite direction. Okay. Now from equation 2 we can derive change this. From 2 we compare to and very clearly this part is the reversible work. So this part must be reversible heat. That means S measures, I should say ds measures change in reversible heat. And we have ds Tds equals to reversible heat. So ds equals to reversible heat divided by some constant temperature. So this is actually how this equation is derived. And in the next lecture, I use a very kind of ad hoc hand waving argument to kind of go to this equation. If we go back there, I actually made a huge assumption. There I kind of argue that for a reversible process with no change, no work. Okay, so if you want to just derive that equation from this statement, it's not enough. It's not enough. So this result, if we derive from here, it's under the assumption that your work is zero. There's no work performed on the system. However, this statement, this equation is more general. You can very generally argue that in this way, it's always true. This is always true. Actually, I expect another question, and one might ask, we actually derive this equation under the condition that there is no the process is adiabatic, right? There is no dq. Actually, when we derive this, we say, okay, it should be, it's adiabatic, so this term goes to 0. Okay, but after we obtain this equation, we know that this applies to all processes, not just adiabatic processes. And also this ds actually measures change in reversible heat, in the heat. Okay, so basically this gives us the contribution from heat and then contribution from work. Contribution from heat, contribution from work. And why is that? Because when we arrive at this equation, we found out that now everything in this equation, I should say, this fundamental equation of thermodynamics, everything in this equation are state variables and the state functions. They do not depend on the path. Okay? So when we derive this equation, we assume we go through a adiabatic path. So we go through a adiabatic path and we obtain this, we kind of calculate all the changes in the system and arrive at this equation. But they are state functions. They only depends on the state variables. So everything here, state variables. Later on, we will actually focus on this and very look at the consequence of this. So since they are from state equations, so you can find any path connecting this change, and your result, your calculation, your result will be the same. Okay, so that's an important and actually very commonly used argument in thermodynamics. To calculate the change in a state function, you find the most convenient path to calculate the values. And then if you go through another path, you will arrive at the same result. Okay? Okay, so now we derive this as a consequence of the second statement. Not using this to derive second statement. Normally in conventional thermodynamics, this has to be defined, given. It's not derived. Okay. Any other questions? So we will talk about consequences of those two results. And the first one I want to talk about is this called maximum entropy principle. Maximum entropy principle. So you see, the second law is very useful in predicting the directionality of reactions. So from the first part, the first part is a inequality. Any spontaneous process under diabatic condition will give rise to an increase in entropy of the system. Okay. Now, since entropy increase leads to spontaneous process, and the spontaneous process will be spontaneous, meaning it will happen. Okay. So another way to look at this inequality is if entropy can be if a system can increase its entropy, it will do so. So as long as the entropy can be increased, a spontaneous process will bring the system to a higher entropy state. So this means equilibrium states are maximum entropy states. So the condition for equilibrium now is understood. The condition for equilibrium is for entropy to reach its maximum. And this maximum, because it's thermodynamics, has to be a global maximum. Okay. Graphically, if we plot some entropy along some direction, some coordinate y, this y can be some variable that can be used to control the system. Okay. And of course, entropy will be some function of this y, and you will see some curve. Yes. I just randomly draw a mountain, yeah. But this mountain has two peaks, right? So you have one maximum here, one maximum here, one maximum here. All these maximum are not equal. Actually, this maximum that is spatial is the global maximum. Okay. So I will say this is y equals to 0, means it's equilibrium. point. And all other point, for example, if system might be prepared at this point, okay, and it might very well stay at that point for a while, but if you given enough time, eventually this system will find a way to go to this more higher entropy maximum, right? So this point is a metastable state, metastable state. And this one is equilibrium state, already state. Another metastable state here, it also will go there. Okay. So, and we can discuss requirement for maximum. In this part, actually, Chandler introduced the concept of internal constraint to give a very detailed discussion on how system falls from a non-equilibrium or metastable state back to its equilibrium state. And from there, he derived maximum entropy principle as well as maximum energy principle. But I'm not going to go into those details. We don't have enough time this semester to do that. So interested students can look it up by yourself. Here, I'm going to give a kind of a simplified version for this. Okay, but it's in the end the results are the same. Just children give a logically more rigorous step there. Now, so if we can define the requirements for maximum, then we can define equilibrium states. So that's the point. We want to be able to determine an equilibrium state of a system. Okay. So from simple mathematics, we know that if this point is a maximum, then any deviation from this point will give rise to a change, a negative change in its value. Okay. So what this means? This means if we start from this maximum, but then we displace the system a little bit, then go to another point and go down here. And let's say this change is delta y. Yeah. So a small perturbation around the equilibrium point. And any small perturbation around the equilibrium point will decrease the entropy. Otherwise, it's not maximum, right? If it's a minimum, then any displacement will increase this function. It's a maximum, so any displacement will decrease the function. So mathematically, we can write down this as a way from y equals to 0, meaning maximum. So the entropy will decrease. So any entropy change, delta S, delta S, under fixed energy, fixed X, then go to delta Y, will lead to a decrease, a negative value. So this is delta Y, and this is delta S. This delta S must be negative. And delta here, this delta means it's a small perturbation, small change, any small change. But not only this, okay, it's more than this. This is basically a first derivative statement, linear displacement. And the square of this displacement, so delta square as second order deviation. Because this must be kind of, it's a maximum, so this must be negative also at this point, at this. So those two are requirements for maximum, and they are the mathematical form of the Maxima entropy principle. Okay. And how do we apply this? Let's try a heat exchange problem. So let's consider a system, two systems, system 1 and system 2. And system 1 will have too small. I want to put bigger. System 1. And system 1 should have its energy. System 1 energy, its temperature, and its entropy. And we have a system 2. And then its energy, E2. Superscripts denotes system 1 or system 2. It's 2. Okay. And we connect this, if we have some heat conductor connecting these two, and through there will be an energy transfer. So if they have a heat exchange, that means the energy can exchange between them. Okay. So if we define delta E1 change in system 1 energy. So energy can go from system 1 to system 2 or from system 2 to system 1. Doesn't matter. Okay, so delta E1, if it's positive, then energy goes into system 1. If it's negative, then system energy goes into system 2 and away from system 1. The same definition here. Okay. And we can also define system 2 change in system 2 energy. But from this scenario, we know that the total system only contains system 1 and system 2. There is nothing else. So energy conservation requires that delta E2 must be minus delta E1. So amount of energy exchange between these two is the same. It's only the directionality, but it's different. Okay. Then, since entropy is extensive, meaning if you have two systems, then their entropy will be, total entropy will be entropy of system 1 plus entropy of system 2. So change in entropy. Now I also write down the total. There's confusion. Yeah. Will be change in energy in the two systems. Okay. And our argument is that the change of energy must be smaller than 0 for around equilibrium point. And how do we calculate the change of energy, the small perturbation in entropy? Sorry, not energy, entropy. So this, how do we estimate this small amount of a change in entropy? Well, if we can write down the first derivative of now, because now energy changes, it's change of energy. So if we know how entropy change with respect to the change in energy, and what is that? That's partial S, partial E. Okay. And it's system 1. And this condition fixed. X is fixed. Now E is not fixed, but X is fixed. Okay. Then times delta E1. Right? Because this change in entropy is induced by change in energy. So we have the first derivative of a change in energy times delta E, calculus. And for system 1 and also for system 2, same equation, but now it's for system 2. And you realize that we see this before. Because temperature, our definition of temperature is partial S, partial E. This is a definition of temperature. This is temperature. Temperature of system 1. This is temperature of system 2. Sorry, inverse temperature. I think I must be careful here. Yeah, inverse temperature here. Partial E, partial S is temperature. So we go back here. This is inverse temperature. Inverse temperature. Inverse temperature. Sorry about that. So let's plug in inverse temperature as well as this equality to rewrite delta E2 as delta E1. So here we have T, sorry, 1 over T1 is, and delta E1 we will keep it. And here is 1 over T2. And delta E2 became minus delta E1. And this minus sign will come here. And this became T1. 1 over T2 delta 1. And we know that maximum entropy principle tells us that this first order change has to be smaller or equals to 0. Equal sign means it's in equilibrium. So we know that condition for equilibrium is now T1 minus T2 inverse delta E1 equals to 0. And in this case, exchange of energy could happen, could be any value. So this must be 0. Must be 0. And for this to be 0, that we know that T1 equals to T2. So thermal equilibrium, according to maximum entropy principle, thermal equilibrium occurs at when this temperature of these two systems are equal. So this is one condition for equilibrium. And then direction of a heat flow. Heat flow here is delta E. Energy change. This small amount of energy changing from one system to another system. So how do we figure out direction of heat flow? Well, we now have this inequality. Must be now we don't need the equal sign. There is a direction and it's non-equilibrium. It's spontaneous. So it's an inequality. Okay. So this now depends on the temperature. So we argue this separately. If system 1 temperature is greater than system 2 temperature, if this is true, then this part is negative. So I will do it slowly. So T1, T2, negative. Then delta E is positive. Just from this inequality. If the opposite, T2 greater than T1, then of course this inverse temperature 1 minus inverse temperature 2 will be greater than 0. And in this case, actually, delta E1 must be smaller than 0. Delta E1 greater than 0 means energy goes into system 1, goes into system. Wait a minute. Delta So this is when, oh, I know where I'm wrong. So this is when away from equilibrium. But now we are actually talking about from a non-equilibrium state, non-equilibrium. So T1 not equals to T2. Okay. So we must be careful here. Yeah. So if we start from a non-equilibrium state, T1 not equals to T2. And what is the direction of heat flow? So I must define the question more carefully. And because now it starts from a non-equilibrium state, the direction, the maximum entropy principle says that the system should go to the total entropy should increase instead of decrease. Opposite direction. Now you are going from a non-equilibrium to an equilibrium state. So in this case, actually, you start from here. So entropy must increase to reach a new equilibrium. So this is greater sign. So then it's opposite. If this is smaller than 0, this must be smaller than 0. This is greater than. Sorry about that. Yeah. But this also reminds everybody that you have to think this through and actually very carefully examine your conditions and your kind of your assumptions before you make any statement or derive anything. Okay. So let's go back here. If T1 equals to T2, T1 is greater than T2, then delta E1 is negative. Delta E1 is negative means energy is going from system 1 to system 2. Okay? So from high temperature to low temperature, it's high temperature, low temperature. So I will note this. So this is high temperature. The second one is now T2 is the high temperature body. And in this case, delta E1 is greater than 0, means energy is coming into system 1. So any one, the first one or second one, the energy goes from high temperature body to low high temperature body to the low temperature body. Okay. So this is also a statement that you very commonly see in many many textbooks on the second law of thermodynamics. Okay, and it's also a valid statement for this. Okay. We will. I think all of you should be able to learn to use this formalism to argue the directionality of a process. That seems very useful. But in this course, actually, we emphasize more on the quantitative aspect of thermodynamics, or the kind of quantitative way how to actually calculate and rigorously relate thermodynamic property to another thermodynamic property. So this will be something I will ask you to think about it, but it's not going to be the only thing we do in the regarding the second law of thermodynamics. Yeah. In undergraduate thermodynamics, normally you do this a lot to argue about the directionality of process. but we will not just stop there on this qualitative statement. We will try to introduce more quantitative results. Okay, so any questions so far? No?
Sorry.
Please.
I wonder why only consider partial S partial E instead of totally differential of S.
Oh, well, this actually is about this experiment. Because in this experiment, we only allow energy
Okay.
to change. We do not have pressure, we do not have volume or things like that.
Okay. Thank you.
Anything else? Okay. Now regarding the second result, dE is TdS minus PdV plus mu dN, this result. This is a rigorous mathematical result. And this result tells us that mathematically, the total derivative of energy is a function of ds, dv, and dn. From calculus, we know that, first of all, energy now must be a function of S and V and N. Because any change in energy can be determined from change in entropy, change in volume, and change in number of particles. So these three variables fully determined the value of energy. And we say that SVN are nature variables of E. The bottom line is it's easy to calculate dE if ds, dv, dn are given. This given could be, if you can measure it experimentally, then you can very easily calculate the change in energy. So if you know the change in entropy, change in volume, change in number of particles, you can calculate energy easily. Second part, second quantitative result of this is, well, we can actually compare this to sort of a total derivative if this is true. If this is true, then we can write down its total derivative from calculus, right? So if this is true, then dE it must be equals to partial E partial S at fixed V and N, and ds plus partial E partial V S and N dV plus partial E partial N now S and V dN. This is from calculus, total derivative. Of E, right? So we can compare this to the fundamental equation of thermodynamics. We realize that this is energy, but of course we define energy from here. This is not surprising. Partial E, partial S. And what's more surprising, or what's more actually useful is, well, this will be minus pressure here, minus pressure. So minus pressure is partial E partial V. Yes. And this will be chemical potential. So chemical potential is partial E partial S. This is very useful actually, and it also tells a lot of mathematical information in it. It contains a lot of mathematical information in it. For one thing, now because minus P is partial E partial V S and N, this means P is interdependent of V. So this pressure actually depends on V. How? Well, it's a first derivative with respect to volume change. They are interdependent. So this P and V and of course here S and T and this mu and N. There are some sort of thermodynamic variables, thermodynamic functions, but they are conjugated. We call this conjugate. They are all, these two are interdependent. S and T are interdependent. Mu and N are interdependent. We call them conjugated pairs. They are conjugated variables. They depend on each other. And actually, each pair corresponds to a form in energy. So this is a form in energy, PV work. This is heat. This is chemical work, chemical energy. Okay. So you realize that this fundamental equation of thermodynamics actually accounts for the change in energy in various forms of work. Okay. And this idea about natural variable and the conjugated pairs can be kind of generalized using some mathematics. So next we must review a few important mathematical results regarding functions. Take it out here. Okay. So these fundamental equations of thermodynamics are very useful, very powerful. But now look at this result we have so far. It's kind of you discover that, well, how to say this? So okay, I'll just say it straight. This equation is very useful, very powerful, but there's a problem in it. In real world, I said it's easy to calculate dE if ds, dV, dN are given. In real world, okay, change in concentration of a chemical species, easy, we can measure that, right? Change in volume, easy, we can measure that. But change in entropy is very difficult to measure. And there is no entropy meter. There is no something that you put in there and it measures entropy for you. Impossible. So this S is not very useful. It's not very easy to control experimentally. That makes this energy function not very convenient. But now we found out that actually S and T are conjugated pair. They are conjugated variables. So S depends on T depends on S. This means we should be able to switch these two variables. So instead of using SVN as natural variable, we should be able to use T temperature, TVN as natural variable. And this process is called Legendre transformation, Legendre transform. So we will introduce this here, a little bit mathematics. Of a Legendre, G E N D R transform, Legendre transform. So generally speaking, let's assume we have a function f, and f is a state function over many variables. So f is a function of let's say s, y, z. Okay, s, y, z. And then change in f can be written as, let's not use s, y, z. Let's use s1, s2, s3, and we can be more, make it general. Yeah, why not? So the change of f can be written as many change over this all this x is called variables times some ui, and we sum over them. And this ui is actually partial f partial xi at all x j not equals to xi fixed. Okay, this is just a general statement from the total derivative of f if f is a function of all those x. And according to what we just mentioned, this means sy, s2, s3 are natural variables of f, natural variables of f. And now this ui and si conjugated. Since they are conjugated, we can calculate. Let's calculate si, ui, si. Derivative of this. So from chain rule, we know that derivative of this is ui dsi plus si dui, right? And this means if we define, we consider, say, df. So basically, let's go back here. df is this. And let's consider just change one conjugate variable. So this actually allows us to change this to switch two conjugate variables. And let's choose one, the spatial one. So I will write df equals to u1 ds1. The first one is the spatial one we want to change. And plus summation I now equals to 2 to some number, ui dsi. We isolate the first one and we want to change this first one. Yeah. And we can actually plug in this ui dsi as duisi minus sidui. And this equation continues, all others I equals to 2. Si ui dsi, yeah, not changed. And here is a total derivative. Here is a total derivative of a function. This is a total derivative of f. We can move them to the same side. So we say df minus d uixi. Now, sorry, now this is not uixi, it's u1s1. u1s1. We isolate the first one. S1 d S1 d u1 the first one. So now it's S1 u1 S1 minus S1 d u1 plus. I'm doing slowly, but it's not anything difficult as actually. So this total derivative of a function, this new function is f minus u1 s1 will be minus s1 I don't know how come I'm so conditioned to write xi there. This is 1, the first one, du1 plus all the rest. And you see that f is a function, natural function of a ds1. F is a natural function of ds of s1. But this new function f minus u1 s1 is a natural function of a u1. We switched the natural variable. So if we define g equals to f minus u1 s1, then dg will be minus s1 du1 plus sum over all the ui dsi. So g is a natural variable of now u1, s2, s3. And this transformation is called Legendre transform. It allows us to change the natural variable of a function, and you can do it one variable by one variable to get other functions. Just give me one more minute. I will just do one thing. Okay, here. So now we have a defined energy. Energy is a natural variable of S3n. And what we want to do here is, entropy is very difficult to measure experimentally. If we can switch this entropy to temperature, it will be much easier. Then according to this Legendre transform, what can we do? We minus these two conjugate variables, S and T, from energy. We can do this. So we can, if we define, this is will code, okay, this will code A. A equals to E minus TS. And we can calculate dA is dE minus TdS minus SdT. dE equals to TdS minus PdV plus mu dN minus TdS minus SdT. TdS cancels out. So you have a minus SdT plus PdV plus mu dN. As expected, now A is a natural function of temperature, volume, and number of particles. And this A is then more useful because if we know temperature, we know volume, we know N, we can very easily calculate A, change in A. And this is more useful than internal energy experimentally. Also, internal energy, one thing that people or students often confuse is actually E energy is also T, a function of T and V and N. But this is not natural variable. So this equation, dE, if we want to connect it to dt, dV, dN, this equation will be complicated. So you can still define energy in terms of temperature, volume, and N, because temperature, volume, and M determines equilibrium state. And at this given equilibrium state, the energy is fixed. Energy is a state function. Okay. But the thing is, temperature is not a natural variable of energy, meaning using change in temperature to calculate change in energy would be complicated. So it's not easy to apply, to calculate energy, to use energy function. If you are working experimentally, you control temperature. So do not say that, okay, now SVN is our natural variables of E, so energy do not depend on temperature. No, that's not true. Of course, energy depends on temperature. Of course, TVN determines energy. It's just the process will be very complicated. And this A is, of course, Helmholtz. We'll talk about this later next time. This is a free energy, or generally called auxiliary function. It's Helmholtz free energy. And you might actually already learn that if we change this natural variable to Tp pressure, and you have a Gibbs free energy. Okay. If we change this to Sp, and we change from this energy, we change from volume to pressure, then we have entropy. So there are auxiliary functions that allow us to calculate thermodynamic properties more easily in given experimental conditions. Okay, I already go over time, so I should stop here. Any questions? Okay, if not, we will stop today's lecture here. So next week we will continue the discussion on free energy. Of course, free energy functions are very important. And then we can if we introduce all the auxiliary functions, then we can very easily show you this, Maxwell relations and other things. Okay. So I think next week, next Tuesday, we should be able to cover most of the thermodynamics part. Yeah. Okay, so we'll stop here and then see you next Tuesday.